Now in this video lecture we will go through impurity defects, right? So impurity defects, as the name suggests, the defects that are developed in the solids may be ionic solids, right, or other covalent solids, due to addition of some external impurities, right? And these added external impurities will also change the properties of the solids, like electrical conduction, right? So let's take example. Suppose this is a crystal lattice. Crystal lattice made up of A and B. A represents cation, B represents anion, right? So this A plus that you have, B minus. Let's connect these, right? Similarly, we have A, then B, then we have A, then again B, right? Suppose this is the crystal lattice. Now when we talk about impurity, if we add, say, impurity of another, if we add another metal impurity, right? Here if I add C plus, say this is a metal cation, right? If I add this C plus to this ionic solid AB, right, then some of the lattice sites, right, of AB, right, would be replaced by this C plus, right, metal C, right? So on adding this impurity of metal C, right, this metal C, what it will do is it will replace some of the metal cations in the crystal lattice, right? So original metal cations would be replaced by these added metal, which we call as impurity, right? Now this added impurity, right, can replace the metal cations at the lattice sites, right? So these impurities may be found at the lattice sites, right? These are lattice sites, or these, instead of going to the lattice, these impurities may go to the interstitial sites, right? So you may also find these impurities over here, right? So this is your interstitial sites. We know interstitial sites are what? These are voids or empty spaces between the particles, right? Particles may be cations, anions, or particles may be your metal atoms, right? So now it's little clear that these impurity defects, right, impurity defects are developed when we add metallic impurities, right, externally, right? So these impurity defects are developed due to added metallic impurities, right, due to added metallic impurities. And this process of adding impurities, right, is known as doping, right? We call it a doping, the process of adding impurities to a crystalline substance so as to change its properties, right? So here one thing is clear, that when we add this external impurity, right, to this crystalline substance, this impurity that is added would also be changing its properties, right? We'll see later. We'll mainly look at the electrical properties, how it will change the electrical conduction of these solids when some external impurity is added to the crystalline solids, right? So now we are also introduced to one more term, which is your doping, right? Doping. Doping is when adding impurities to crystalline substances, right? That may result into the change of the properties of crystalline substances, right? Now let's take example, and we'll also look at how the addition of impurities will result into the change of properties, right? So these impurity defects, right? We would be dealing with impurity defects. First we'll go in little in detail with ionic solids, then we'll go with covalent solids, right? So with ionic solids we'll take example of sodium chloride, right? Suppose this is your sodium chloride lattice, right? Sodium chloride lattice. Right. Now if I add impurity, let's say we add impurity of this Sr2 plus, right? Then what will happen? Since I'm adding this Sr2 plus, it has charge which is double of the charge that is present on sodium, right? So if I introduce this impurity, this is an impurity, right? If I introduce this impurity to this crystalline solid, right, to this crystal of sodium chloride, then the introduction of Sr2 plus, right, introduction of Sr2 plus will replace two sodium ions, right? It will replace two sodium ions. Why? Introduction of one Sr2 plus will replace two sodium ions. Why? To maintain the electrical neutrality, right? So this will Sr2 plus will replace, we have done this in the previous lecture also, Sr2 plus will replace two sodium ions to maintain electrical neutrality, right? Why two sodium ions would be replaced? Because we know that Sr has 2 plus charge, right? And 2 plus charge is equivalent to, this 2 plus charge is equivalent to 2 charges on 2 sodium ions, right? 1 plus is equals to 2, right? Now this Sr2 plus, right? Since introduction of Sr2 plus in this crystal of sodium chloride will replace these two sodium ions, right? These two sodium ions or sodium metal at its lattice site. So now these two sites will become empty. These two lattice site will become empty on introduction of Sr2 plus impurity, right? So one of the lattice site would be occupied by Sr2 plus like this, right? And other will remain empty. It will remain like this only, right? So one would be replaced by Sr2 plus and other will remain empty, right? And this is your, what do we call to this empty site? We call it a vacancy, right? Like we have done before, vacancy defects, right? So one of these lattice sites is occupied by Sr2 plus and the other remains vacant, right? And these vacancies result in higher electrical conductivity, right? So because initially we said that the addition of impurity will gonna change the electrical property of these solids, right? So due to this vacant site, this vacant site will increase the electrical conductivity of this crystalline solid, right? So I'll mention it over here. So we'll replace two sodium ions to maintain electrical neutrality. Two sodium ions would be replaced, right? Two sodium ions would be replaced so now we have two empty lattice sites, right, or vacant lattice sites. One lattice site would be occupied by Sr plus 2, right, and other will remain vacant, right? And it is due to this vacant site that electrical conduction of ionic solid will increase. Right? It is due to this vacant site that electrical conduction will increase. Right? So this is your introduction of impurity defect in ionic solids, right? And same thing would be observed here. We have taken example of Sr2 plus in sodium chloride. So if you introduce, the similar thing would be observed if CdCl2 cadmium chloride is added to silver chloride, right? Here this silver has one positive, right, one positive charge, and cadmium has 2 plus. So when you introduce cadmium chloride impurity to silver chloride, two silver ions would be replaced by, when you introduce cadmium chloride, the introduction of cadmium ion will replace two silver ions, right? One. So now after these two silver ions would be replaced, we have two vacant sites of these silver ions. One would be occupied by this Cd plus, one would be occupied by this ion, right, divalent ion, and other will remain vacant, right, same as this. Now this was the case of ionic solids, right? Now let's take another case of covalent solids. Now we'll take the case of covalent solids. Covalent solids like germanium and silicon. These are group, if you remember the periodic table, these are group 14 elements. Right, germanium and silicon, these are group 14 elements, and they have 4 electrons in their outermost shell, like this. So if they have four, both these have 4 valence electrons, right? That means this germanium, if you look at the covalent structure of this germanium, or if you look at the covalent bonding in this covalent solid germanium or the silicon, both have 4 valence electrons, right? So this will look like this, right? And it will make bond with all neighboring atoms, all neighboring germanium atoms, right, like this. So this is how bonding takes place. We are already familiar with bonding, right? This is how bonding in germanium looks like, because one germanium atom has 4 valence electrons, so it will form 4 bonds with neighboring germanium atoms, right? Now let's see how the addition of impurities can affect the properties of this covalent solid, which is germanium, right? So now we are dealing with addition of impurities to covalent solids, right? So doping, this again we know the term is doping when we add impurities to these solids, right? So So in these covalent solids, right, like germanium, we said germanium and silicon, we can add two types of impurities, right? We can add two types of impurities. One is since this germanium has 4 valence electrons, so I can add one type of atom, right? One type of atom that has less than 4 electrons in its valence shell, right? For example, group 13 elements like aluminium, gallium, right? They have 3 electrons in their valence shell, which is less than 4, right, of this atom germanium. The other type of impurity is your impurity that has more electrons, more valence electrons than germanium, right? For example, arsenic. Arsenic has 5 valence electrons, right? And arsenic we know is your group 15 elements. If I remember, arsenic belongs to group 15, right? Phosphorus, arsenic, all these have 5 electrons in their outermost shell, and this comes under group 15, right? So impurity like arsenic that has more electrons than germanium is called electron rich impurity, right? And impurity like aluminium or gallium that has less valence electrons compared to germanium is called electron deficient impurities, right? So to covalent solids we can add two types of impurities. One is electron rich impurity and other is electron deficient impurities, right? So to covalent solids we can add two types of impurities. Let's just do it over here. Two type of impurities. Covalent solids like germanium or silicon, right? Both have 4 valence electrons, right, and belong to group 14 in periodic table. You can add either electron rich impurities, you can, or we say you can dope germanium with electron rich impurities, right, which is your arsenic or phosphorus, which belongs to group, this belong to group 16, right? I'm sorry, this belong to group 15, right? These are electron rich impurities and belong to group 15 elements, right? And the other is you can add electron deficient impurities. You call it as aluminium, example aluminium or gallium. Aluminium or gallium that belongs to periodic, that belongs to group 13 of periodic table, right? And it has 3 valence electrons, and this one has 5 valence electrons, right? So this one is electron rich because arsenic has 1 electron more in the valence shell than germanium, and this is electron deficient impurity because this aluminium has 3 valence electrons, which is 1 less than germanium. Now let's see what is the effect on the bonding, right? Now before we go ahead and look how doping will affect the electrical property of germanium, let's just do one thing. Let's understand one thing. We know that germanium or silicon are non-conductors, right? Are non-conductors of electricity, right? Because these are covalent solids, right? Because they do not have any free electrons, because we can see that all the valence electrons or germanium are used up in bonding with all neighboring germanium atoms, right? So no free electrons, no electrical conduction. But if we heat this solid germanium, then some of the bonds at high temperature bond will break. Bond will break to release electrons, right? So once we have electrons as a result of this bond dissociation between two germanium atoms, we have electrical conduction, right? Electricity will start conducting once we heat this solid, right? Because heating will result into dissociation of this bond, and dissociation of bond will result into free mobile electrons. And we know that electrical conduction is due to free mobile electrons. So this is one way using which we can make these solids to conduct electricity, right? And this is known as intrinsic semiconduction, right? This is your intrinsic when electricity is conducted in this way, when this solid is heated, this is known as intrinsic semiconductor. Intrinsic semiconduction, right? And this solid would be called as intrinsic semiconductor, right? Now there is another way we can make this solid electrically good conductor, right? The other way is by adding impurity, right? By doping this metal. Let's quickly see. Now if I add, say, this arsenic to germanium, we know that arsenic has this As, right? This As has 5 valence electrons, right? So 4 of the valence electrons, if arsenic say will occupy this site of germanium, right? 4 of its valence electrons will form bonds with neighboring germanium atoms, right? Since it has 5 valence electrons, this is an electron rich impurity. One will, let's represent it with X, one will remain free, right? One is still not used. This is known as an extra electron, and we know this is mobile electron, right? So since now, on introducing this impurity, this electron rich impurity of arsenic, right, that has 5 valence electron, right? Now we have free mobile electrons due to addition of this impurity. Since we have mobile electrons, so electrical conductivity will increase due to the addition of this external impurity arsenic, right? And since this is due to this electrical conduction is due to these negative electrons, we call these arsenic doped germanium is this is when you add arsenic to it, right? When arsenic is added, we call it arsenic doped germanium, right? And this arsenic doped germanium, once you add arsenic, will become a semiconductor, right? Since it has become semiconductor due to this negative electron, we call it a n-type semiconductor. Right? And we know that semiconductors are used in many ways, right? So this is how the arsenic doped germanium begins to exhibit fairly high electrical conductivity, right? This is how this now germanium will start conducting electricity, right? Now you have to remember one important thing in this, that the electrical conduction has occurred due to the free electron, right? That has not resulted into bonding. That's a mobile electron, and we know that due to mobile electrons, electricity is conducted, right? Now we have, and this type of semiconductor is your n-type semiconductor. As I said, that since this is due to negative electron, so we call it n-type semiconductor. N stands for negative, right? So now we'll look at the other impurity, which is your electron deficient impurity. Electron deficient impurity, when we say by electron deficient impurity, we mean that the valence electrons in the impurity right, would be less compared to this germanium, right? Compared to germanium, the electron in, we know that aluminium has 3 valence electrons, right, like this, right? So let's say if you add aluminium here to germanium, it has 3 valence electrons, right? 3 of its valence electrons will form bond with 3 of the valence electrons of aluminium will form bonds with neighboring 3 germanium atoms, right? And one site, right, one of the site is vacant, right? One of the site is vacant. So this is your group 13 element. Aluminium is a group 13 element, right? So when germanium is doped with aluminium, right, then at some lattice points, the lattice points where the lattice points that are substituted by aluminium or gallium, right? Gallium also has 3 valence electrons. Now group 13 elements have only 3 valence electrons, right? They can form 3 covalent bonds. Like you can see here, this aluminium has formed 3 covalent bonds, 1, 2 and 3, right? Like germanium, it cannot form 4 covalent bonds since it has only 3 valence electrons. So bonds with neighboring, it formed 3 bonds with neighboring germanium atoms, right? Thus a hole is created at the site where 4th valence electron is missing. This is your electron vacancy or electron hole, right? Here where you don't have any electron, here this is a vacant site kind of, right? Here electron hole or vacancy is created, right? Since it does not have 4 electrons, right? So here a vacancy is created. An electron, so now what will happen is that an electron, since this is a vacant, since this is vacant, this should be occupied by an electron. Now since there is no electron, we call it a electron hole or electron vacancy, right? Now to take place of this vacancy, electron from neighboring atom will jump into this vacant site, right? So we say electron from neighboring atom will jump to occupy this vacant site, right? So when electron, say from here, will jump into this vacant site, now this, from its original place, the electron will jump from here, right, to this place. So this place will become vacant now, right? And after electron will move to this vacant site, this will become vacant now. Now to take place of this vacant site, say electron from here will jump to this vacant site. So this way, now when electron will jump from here to here, this will become vacant. Now to take place of this vacant site, electron from here will jump. So you see that electron will start flowing, right? In a way, this hole is moving, right? So when you apply electric current to this system, the moving electron will be attracted towards positive plate, and this hole, right, would move towards negative plate. So this way electrical conduction will stop. So we say that addition of this electron deficient impurity has increased the electrical conductivity and had made it a semiconductor. Now we will call it a semiconductor, right? Since the hole is we call it a positive vacancy, right? Since this is a vacant place, so we call it a positive vacancy. So this is a positive hole, right? We also call it a positive hole, right? Since the electrical conduction is due to this positive hole, because due to this positive hole only, the electrons are jumping to take its place, right? So in a way, this hole is moving. Since this hole is positive, we say this is positive. We call it, this semiconductor would be called as p-type semiconductor. We call it a p-type semiconductor. P is due to the positive hole, right? So this is a p-type semiconductor. So this has also resulted into